So we got to this example before coffee, and despite all my wittering and second guessing, this is the thing that we need you to be able to do, right? Even though it doesn't necessarily seem a logical thing to do, this is the way to answer this problem. And so if we give you one of these, and you're likely to see one of these like in the multi-choice question maybe, or in the final exam, if we give you a pair of redox couples, you just go looking for the biggest one, and the biggest one will correspond to the reduction in the favoured reaction, and the other one must therefore be the oxidation, right? Write down the equations, add them up, done. And so in general what we can say is that the favoured reaction, and you'll note I'm not using the word spontaneous because I don't want to yet, even though you've probably seen this, but spontaneous at university refers to another thing. Well, there's a different way of defining what a spontaneous reaction is, and we're not going to do that in bridging. So I'm not going to say spontaneous, I'll say the favoured reaction will be between the oxidant from the redox couple with the more positive reduction potential and the reductant from the redox couple with the less positive reduction potential. Okay, so if you go back to that slide where we said that in the redox couple the thing on the left is the oxidant and the thing on the right is the reductant, then the favoured reaction will be between the oxidant from the redox couple with the more positive E standard and the reductant from the redox couple with the less positive E standard. Right, so for the rest of today, we want to focus on how you experimentally determine what these reduction potential values are. Right? And so the method that you use is by building something called a galvanic cell. So we've seen that the reduction potential values, the E standard values, give us an idea of how strong an oxidant is. So in other words, how much the thing wants to get electrons and so be reduced. And as we've seen, you can go to books, your SI chemical data book or textbooks or whatever, and they'll have tables of these things in there. And so normally you can just go and look up the number you want and just use it and you're away. But those numbers have to come from somewhere. And so that's what we're going to look at now. Okay. So if we then go and consider the reaction that we were talking about yesterday. The zinc reacting with the copper 2 plus to give zinc 2 plus and copper. And so we know from last week, we know from yesterday, that this redox reaction involves the following half equations. So zinc going to zinc 2 plus 2 electrons, that's your oxidation, and copper 2 plus gains 2 electrons to make copper. And so the overall reaction is zinc losing electrons, or if you like, the zinc giving its electrons to the copper 2 plus ions. The copper 2 plus ions gets those electrons and turns into copper. Yeah? So during the reaction, we can say that electrons are transferred from the zinc to the copper 2 plus. Yeah? The zinc loses them, the copper 2 plus gains them. So we can think about the electrons being transferred from the zinc to the copper 2 plus. Note that both the copper 2 plus and the zinc 2 plus, under the right circumstances, will be able to gain electrons and turn into copper or zinc. Right? These reduction potentials, these numbers, which we can put on these things, tell you that both the copper 2 plus and the zinc 2 plus have this inherent need to get electrons. And so given the chance, they both will get electrons and turn into and be reduced. Yeah? But in this particular reaction, it's the copper that wants them more. And so it's the copper that gets the electrons, and so it's the copper 2 plus that gets the electrons, and so it's the copper 2 plus that's reduced. It's the best oxidant. Right? This is what we've been saying earlier. You can prove that by the numbers, or you can prove it by just doing the reaction. Yeah? And so we come to my infamous small attempt to do animations in PowerPoint. Let's imagine that we have a tug of war, right? and this is going to somewhat date my slide, but nonetheless. And let's imagine that on one team we had two Jonah Lomus. Jonah's so old now, he possibly half of you don't even know he used to play rugby, but nonetheless, he used to play rugby. In fact, I can remember when he used to be crap at rugby. But there it is. So let's imagine on one side we have two Jonah Lomus, and on the other side we have two Jonah Lomus. And if we start doing the tug of war, okay, look at that. They will go backwards and forwards, but because you have the same number of people on each side and they're the same people, the pulling power on each side is the same. And so overall, we're not going to go anywhere. They're just going to go back and forward and back and forward and back and forward. Right? If you then add a third Jonah Lomu to one side, you kind of know what happens, right? Now the team of Jonahs on the right-hand side has more pulling power than the team of Jonahs on the left-hand side, and so they win. Right? So both sides are pulling, and this is the key thing, right? In this tug of war, both sides are pulling on the rope, but one side pulls more, and so they're the ones who win. And so this is kind of what I'm trying to get at with these redox reactions. You have two different redox couples, both of which inherently want electrons, but one of them wants them more. Now the way that we can start working out what these numbers are to quantify how much more one of the redox couples wants electrons than the other is if we can, if you like, put the electrons on either end of a rope. Put these redox couples on the end of a rope like a tug of war. And the way that we do that is by building one of these things called a galvanic cell. And the galvanic cell is named after Mr. Galvani, who was an Italian chemist back in the 18th century. Again, this interesting time I talked about last week, he's died in 1798. So he's right around that sort of 1780, 1719 period where all the interesting stuff was starting to happen in chemistry. Galvani was the guy who did the frogs' legs thing. Yeah? Has anyone heard about that? There's these nice little engravings of him with a sort of lab bench with all these half dismembered frogs. He was the one who discovered that nerves work by electricity. So if he took one of these fancy new inventions at the time called a battery and attached the wires to the frog's legs, they all jumped around and stuff. There she did. Okay. So here comes a galvanic cell for trying to understand what's going on with the copper reaction and with the zinc. So what we're going to do is we're going to make a beaker. We're not going to make a beaker, we're going to get a beaker. And in the beaker, we're going to pour some zinc ions, a solution of zinc ions. So it could be zinc sulfate, it could be zinc nitrate, it probably doesn't matter. But the concentration of that solution is going to be 1 mole per litre. Right? Standard concentration. And then into that beaker, sorry. We're then going to take a second beaker and we're going to pour into that second beaker a solution of copper 2+ ions. And again, copper sulfate, copper nitrate, doesn't matter. But the concentration of the copper 2+ ions will be 1 mole per litre as well. Right? So both of these solutions are standard concentration. And then, into our beaker with our zinc ions, we're going to put a piece of zinc, which could be as boring as a galvanized nail, but could be a piece of zinc itself. And into the copper beaker, we're going to put a piece of copper. Okay, so what we've got now then on the left-hand side are the two components of our redox couple for zinc 2+ and zinc. Yeah? We've got zinc 2+ ions in the beaker, and we've got a piece of zinc metal. So in theory, when we do our redox reaction, we could have zinc 2+ ions turning into zinc, or zinc turning into zinc 2+ ions. Either would be fine, because we've got both of those things present now. Yeah? And the same with the copper. We've got copper 2 plus and we've got copper. So we've got both parts of our redox couple there. And then what we do is this. We're going to connect our two pieces of metal, the copper and the zinc, to each other with a wire, which will conduct electrons. Yeah? And in the middle of that wire, we're going to put a voltmeter. The voltmeter is going to tell us two things, which we're going to get to in a minute. Right? So we connect our pieces of metal together with a wire, and in the middle of that wire, we have a voltmeter. And then the last thing we have to do is we have to put in something called a salt bridge, which can be horribly complicated or could just be a piece of wet filter paper. But the salt bridge is wet with a solution of some ion, of some ionic compound. So say potassium chloride. Okay? And so those of you who've done physics at school might recognize that what we've done now is we've completed our circuit. And so what will happen now is that when we've connected this all up, the redox reaction will happen. But key to this now, rather than doing everything in the one beaker, is that now the electron transfer reaction will involve electrons being transferred from one side of our galvanic cell to the other. It's not this intimate electron transfer between the reactants and the products in the beaker. We've separated them out. We've put them at either end of our rope in our tug of war now. So now we can use our voltmeter to try and understand how the electrons are being transferred and how much they want to go one way or another. Yeah? So we hook all this up, and what we find is this. First of all, the voltmeter reads you a positive value. That's not written on that slide, but you should write that down. It's going to be in lots more slides, but write it down now, right? A positive value. And what that tells you is that the right-hand electrode, the piece of copper, which is called an electrode, yeah, is what we call the positive one. So the sign of the reading on the voltmeter is the same as the sign on the right-hand electrode. This may be different to what you have heard before, but this is the way we do it here, right? If the piece of copper is the positive electrode, then the piece of zinc must be the negative electrode, right? So we work that out based on the sign of the reading on our voltmeter. If the voltmeter reads positive, and so the copper is the positive electrode and the zinc is the negative electrode, then what that tells you is that the electrons are going this way. They're going from the left-hand side to the right-hand side. If you like, the electrons which are negative are attracted to the positive electrode. Okay. Hello.
Is the reading on the voltmeter the same as the charge on the copper electrode?
Yeah, except I'd probably prefer that you didn't call it the charge on the copper, because that normally means something else. Just call it the positive electrode, not positively charged electrode. Just call it positive electrode. That's probably safest.
So what does the voltmeter value?
What will the value mean?
Yeah,
Or
the voltmeter.
if say it reads plus 1 volt, that tells you that the right-hand electrode is positive. If it read negative 1 volt, that would tell you that the right-hand electrode is negative. Yeah?
Does that mean you've got it round the wrong way?
Does that mean you've got it round the wrong way?
Yeah, it's negative.
Thank you for asking that. No. This is exactly the sort of nonsense they teach you at school. No. It just means it's different. It's not wrong. Yeah? Okay, so if the voltmeter reads positive, that means the right-hand electrode is positive. That means the electrons are going to the right-hand side of your galvanic cell. Now, what does that mean in terms of the chemistry? What it means, hopefully you can read this at the bottom, is that on the zinc side, the electrons are going out of the zinc side and over to the copper side, so the zinc side must be where the oxidation's happening. We must be doing a reaction which produces electrons which can then beetle their way across to the other side. And so over here, we must have the zinc metal turning into zinc 2+ ions and 2 electrons. And those electrons are the ones that travel up and through the wire to the other side. Yeah? So on the left-hand side, we have the oxidation. On the right-hand side, then, we will have the reaction which requires the electrons that are coming in through the wire. So the right-hand side will be where the reduction occurs. The copper 2+ gains those electrons coming in through the wire and turns into copper metal. Are we happy with this? So, we hook up our galvanic cell, we build it like this. Note that it doesn't matter which side you put the zinc on and the copper on. It doesn't matter. It's just like if you had it sitting there and then you walked around the other side of it. It doesn't change what's going on. Yeah? You attach your voltmeter, you look at the reading on the voltmeter. It will read a number. We're coming to what the number means in a minute. But the number will have a sign. It will be positive or negative. If it's positive, then the right-hand electrode is positive. That means it's where the electrons are going to. That means that the right-hand side will be where the reduction half equation is happening. Yeah?
Would this mean that the mass of the electrodes would change?
Absolutely.
The zinc one's dissolving and the copper one's gaining?
Yes, indeed. So that if you were to run this for some period of time and then stop it and pull the electrodes out, the zinc one would weigh less than when you started, and the copper one would weigh more. That's exactly right. Yeah. If you attach the voltmeter and the reading on the voltmeter is a negative number, then that means that the sign on the right-hand electrode is negative. That means the electrons are going away from that side to the other side. So that means that in the right-hand side you have the oxidation occurring. Right? You see how this works? You could argue this is just another set of stuff you have to learn different to what you did at school, but nonetheless, this is the stuff you need to know for here, for this year. Right? So the sign on the voltmeter gives you whether the, I just about said charge then, the polarity of the right-hand electrode, whether it's positive or negative. And if it's the positive electrode, that's where the reduction occurs. Whereas if it's the negative electrode, that's where the oxidation occurs. Yeah? We're happy so far? Just check. This might be on another slide, but just in case it's not, I'll mention this now. This business about the salt bridge, when this reaction happens and you're taking zinc, so you start off with a solution, say, of zinc sulfate, ZnSO4, say. So you've got zinc ions and you've got sulfate ions in here, and you're going to have the same numbers of each, right? Because ZnSO4 gives zinc 2 plus and SO4 2 minus. So when you start off, you're going to have the same number of cations and anions in this solution. But when this reaction starts, this reaction produces more zinc 2 plus. And so you're going to start filling up the solution with cations. But you don't have any more sulfates. So the charges are going to become unbalanced in that solution, and that won't work, right? You can't have a charged solution. So your galvanic cell will stop working. And so what you do instead is you have this salt bridge, which has, say, potassium chloride in it. And what that will mean is that every time this reaction happens and you make another zinc 2 plus ion in here, 2 chlorides from your salt bridge will leak into the solution as well to keep those charges balanced. Yeah? And over here, each time a copper 2 plus reacts and turns into copper, you're taking away a cation out of this solution. And so some of the potassiums from your salt bridge will drop down into the solution to replace them, to keep that solution balanced for charges as well. Does that make sense? Yeah? So if you just have water, if you just have wet paper, or just water in your salt bridge, then it won't work. You have to have an ionic solid dissolved up in water or somehow, and use that as your salt bridge. So you have these ions that can replace the ions that are disappearing or being made. That was a very unhelpful sentence. Do you get what I'm saying? Yeah? You're going to build some of these in the lab next week, so hopefully this will be a chance to sort of get the idea of this. So we can measure, oh, and there you go. So we can measure that the copper electrode has a positive charge. Never mind. I would probably still prefer that you say we can measure that the copper electrode is positive, but whatever. This means that this is the electrode to which the electrons are moving. So this is the electrode at which the reduction is occurring. So the positive electrode is where you get the reduction. In NCA chemistry, this is called the cathode. We do not use these words here. We don't say cathode and anode. We haven't done for a long time, I think because we used to teach electrolysis, and those of you who've done high school chemistry here will know that when you do electrolysis, the cathode becomes the other thing, and the anode becomes the other thing, and it all gets horribly complicated, so we just don't bother. Right?
How can we still do it in school?
I don't know, because we have... Well, see, there's this underlying premise, I think, that NCEA prepares you for university. Otherwise, why would you do level 3 chemistry, really? And yet no one who puts together the NCEA syllabus actually communicates with the universities. You would think they would. That would make sense. Sorry. It's like where's my friend who got told we don't do aqueous solutions here? Heaven help us. That's just... The zinc electrode is the negative one. See, that's better. I like that better. The zinc electrode is the negative one, and so is where the electrons are leaving from. And so the negative electrode is where you get your oxidation occurring, and this is called the anode in high school language, right? So we talk about positive and negative electrodes rather than cathodes and anodes. It's kind of the same deal. I don't really mind if you think about it as being cathodes and anodes, but you're not going to see us use those words here. Okay. Hello.
You said that's the electrode where the reduction is occurring. The
Yep.
reduction is occurring in the solution, though, rather than on the electrode itself. The reduction was occurring on the electrode itself.
I see what you're saying. The species in the solution are the ones that gain the electrodes. Yes, that is true. So what we're going to see is sometimes the electrode itself doesn't actually part of the redox couple. Yeah, but none of it's just the way we say it. Yeah. Okay. So So instead of drawing these little pictures, obviously the pictures take a little while to draw, and we don't always want to be doing artwork. So there's a system that has been developed where we can write like a shorthand to describe this picture. It's called a cell diagram, and for this one it looks like this. And so what we do is we write just a string of stuff where the stuff on the left-hand side corresponds to what's on the left-hand side of your galvanic cell, and the stuff on the right-hand side corresponds to what's on the right-hand side of your galvanic cell. And the convention is that we start with writing the electrode, or if you like, well, at least the thing that you attach the wire to goes out here. So in the left-hand side, the thing that the wire is attached to is the zinc metal, so that's the one that goes first. Then we have a line, and that can either be a sort of a slanty line or just a horizontal line. And then we have the other part of our thing, the thing which is in solution here. So the zinc 2+, then we've got brackets aqueous, comma, C standard. Now that C standard indicates that that's at standard concentration, 1 mole per litre, right? And then we have this double line, and the double line indicates the salt bridge. And then we have the things on the other side. We have the thing that's in the solution, the copper 2+, aqueous at C standard, and then another line, and then the copper electrode. So the single line indicates the two things separated by a single line are in a different state. So solids separated from ions in solution, or solids separated from gases, or that sort of thing, right? If you have two ions in solution, then you have them together but separated by a comma. There's an example of that towards the end, right? So in general, we have the redox couple on the left-hand side here, with the thing on the outside being the thing that the wire is attached to, and then separated from the other side by double lines, which indicates the salt bridge. Yeah? So that's what all of that says.